should work.
I'll just grab us something to drink.
Let's do a sound check real quick. Noise, noise, noise. Noise, noise, noise. Oh, this is also muted. Checking sound. Checking sound. Oh, that sounds terrible. Wait, should it sound that bad? Oh, that sounds terrible. Oh, that's fine, okay. got a YouTube strike for playing someone else's video on live.
Oh, really?
Yeah. I should have. It makes sense in hindsight. Amber works for Google, right? They're probably extremely sensitive about that. So I'm going to make sure. I'm in trouble, but not that much trouble, right? So I restarted, and we have just right now. Okay. Cool. Well, you know, I thought it was open source. That'll be what I claim, you know.
YouTube.
I assumed the public talk about open source was something I was allowed to show. And I didn't even say it was mine, right? I introduced Amber. Okay. So let's see. I believe, I'm not 100% sure. I didn't know Amber personally. There was someone I went to school with who shared that video, even though it was near me. So I think Amber lives in San Francisco and just came up for the talk. And I didn't know about it. I wasn't there live. But I think there's this sort of mixed team at Google that's like the Android project, but they also do programming languages. And I think that's what she's on. So I think they do RISC-V, Rust, and then just a ton of open source stuff. Until the cloud really blew up, Android was the biggest open source OS. Now it's almost certainly Ubuntu on all the containers, but I don't know. Okay, so Finite Automata, right? Or Finite Automata. Well, I'm going to teach you, so we don't need to introduce that yet. Okay. Here's one way to think of the theory of computation, and it's chronologically, right? So basically at some point in time, and for me the inflection point is 1959 with the invention of the first programming language, Fortran, followed shortly in 60 by Lisp and 69 by C. And fundamentally those are the only programming languages that matter. A lot of the development of Python over the past few years has been making it able to do all of the things that Lisp does, right? And you could equivalently argue that most C is written with such extensive preprocessor that they've essentially implemented Lisp inside of C, right? Fortran is not a real language in the classical sense, right? It wasn't durable the way Lisp and C were, right? But by around that time, right, people were starting to write down text and give it to a device, and the device would create some computation, and it was much more similar to typing keys into a calculator than it was to sort of abstract maths and thinking about something like group theory or ring theory or elliptic curves or something, right? That's in the 60s, right? And computer science predates that, though not by much, right? It was maybe a subfield of mathematics in the way that's I don't know, what's another subfield of mathematics? Cryptography, something like that, right? So it was around, people were studying it, but they were just mathematical objects. So there's this 1930 to 1950s range, sort of beginning with Gödel's general recursive functions and Alonzo Church's lambda calculus in 1929 and 1933, respectively. And then culminating with Alan Turing's description of the Turing machine the same year, 1936, is Post's description of Post's essentially a Turing machine, right? And so there were these people that were thinking about creating mathematical objects that could compute many years before the first physical ones came into form, right? And that's sort of the inversion of, I think, the Amber method, where it's in 2013, there was this human that discovered there was an existing algorithm that could run on hardware. In the 30s, it was going the other way. It's they had these ideas, they were trying to get them to run on hardware, and they started making things with tapes and gears and levers and so on, right? Why does this matter? Well, many of the original theoretical results demonstrated over these mathematical objects still apply to our actual existing physical devices. I'm going to tease out some places where I think things are a little bit different. The cloud is not fundamentally different in any important way than a lot of Turing machines that are all interfacing with each other, but it gets to the point where if you're running everything in containers under Kubernetes on cloud servers, it's are we really going to think that that is a Turing machine? You can. So I'll tease at that a little bit, but we're going to begin with this 30s to 50s era, and we're going to demonstrate some properties about automata that are useful to us. And I think the two most important results that come out of automata theory are undecidability and halting problem. And one of the reasons for that is, my understanding is, especially in earlier computer science, before people got used to it, it was commonly the case where a business manager would come to a computer scientist and ask that computer scientist to do something that you can actually prove is impossible. It would be very nice, for example, to just write the computer program that causes the clocks on every computer on Earth to be perfectly synchronized. And that's provably impossible, right? So we have to make sure whenever we're writing our computer programs, we don't set out to do something that is provably impossible. So this is the theory of computation. Oops, I went too far. If we had computers, what could they do? How fast could they be? Could they, do they have to be deterministic? How much memory do they need to solve certain problems? Are there types of information we can and can't encode to them? So right at the end of this weekend, we will get right up to the point of looking at the difference between the natural, rational, and real numbers. And of course, the natural and rational numbers. Hello. Oh, thank you. That would be great. I was overheated. I don't know if you were, so I asked for something. Thanks.
It's about as good as I can do for now.
That's perfect. See, I'm going to plug that in here. Cool. Thank you. Anything else? Thank you for stopping by. Let's see how loud it is.
You can put it on the top so you can.
Yeah. We'll use it during breaks. Okay. Are you overheated? Are you okay?
I'm fine.
Yeah. You're tougher than me. Okay.
Yeah, I'm sure. This is perfect weather for.
Okay, perfect.
For me.
I won't complain then. Automata is, generally speaking, the name used to refer to the models of computers. One thing I want to address is that I'm going to talk a little bit about automata, languages, and grammars. We generally regard automata as a mathematical object, in a way a function, that receives some input, which is not really necessarily the inputs to the function because it can have an arbitrary number of arguments of different types, and then it just produces a true-false outcome. So it's sort of a function from something to 0, 1. Grammars are different. Grammars are usually generators, so they generate a language. We are going to show that we can have like an equivalent grammar and automata, but the difference is the automata accepts the language or recognizes the language, and the grammar generates the language. So basically this is the mathematicians coming at it from one side got this notion of recognition, and the linguists coming at it from the other side got this notion of generation, and then they were found to be equivalent in the 30s through 50s. And then once they were equivalent, that gives you the new field of computer science, right? So here's our first example. Say we have a computer, and we define this computer in some formal way. For example, we say, I have 4 gigabytes of RAM. Those 4 gigabytes, giga is 1,000 mega, a mega is 1,000,000 bytes, so I have 4 billion bytes. But they're not exactly 4 billion bytes, right? Because we approximate 1,000 with 2 to the 10th, which means it's 10 to the 24th to the 10 to the
24.
Yeah, why did I say 24? 24 doesn't make sense. It's 10 2 to the 30th. There we go. Times 4. Which is 1024. I said 10 to the 24 instead of 1024.
1024.
Yeah. Oh my gosh. It's too early in the morning for me to be doing mental gymnastics, right? That. So you have some fixed number of bits, right? You can say, well, that fixed number of bits, we can map that to a subset of the natural numbers, and we can just say every single natural number corresponds to 0 or 1. We just write some mapping, yeah. And perhaps that's our formal model of a computer, right? Okay. So say we have a sorting algorithm. Oh, this is, again, easy to define, right? We say, well, of my 2 to the 32, oh, that's why they have 4 gigabyte RAM, because it's 2 to the 32. Okay, so of my 2 to the 32 bits, right, I break each of them into chunks of size 8, 16, 32, 64, doesn't matter, right? And I say, well, actually, instead of taking one very large number with billions of digits, right? I will say, well, I have actually many small numbers that can be up to in size 4 billion, which is 2 to the 32, right? And what I want to do is I want to see if, given that input, is there some way to know if whatever my device has that's running, whatever my mapping is, it checks to see if each one of those chunks is in order. So the lowest, or the first 32 bits, contains the binary representation of the smallest value, and then the highest contains the largest value, right? And perhaps you're not required to use all of memory, right? So you say, oh, after a certain point, if there's just a bunch of zeros, we don't interpret that as an additional number. We say that means we've reached the end of our array. Can we write a specification for that? Well, no, actually. There's no way to demonstrate the equivalence between a model of computation and a specification, because that's actually a recursive problem. The specification, to be fully specific, would be equivalent to the program itself, and then you're not demonstrating the equivalence between anything. You just have a way of writing it down. It's just a program. There is this notion of the Curry-Howard correspondence that you can convert programs to proofs and back and forth. So you can say it is a proof of something, but you can't say it is a proof that this computer implements this computing algorithm. Here's another example. I updated this last night. So the slide said Gemini, and I was like, why'd they say Gemini instead of DeepSeek?
DeepSeek.
Yeah. And then we just watched Amber's talk, and she was talking specifically about Gemini, and I was like, oh, it was a reference. Anyways, so say we have a really, really optimized LLM. We have a program we would like to run on our computer, but we don't know if we actually have enough computing power to run it. Can we ask the LLM if it can run the program? Well, we can't actually determine this, right? Because the only way to determine whether your program will ever finish running is to run it and see if it stops. But that only tells us if it stops.
If it stops, if it doesn't, then...
If it doesn't stop, then we don't know if it's about to stop. We don't know if we're 1 nanosecond before it completing its computation. And it is true we can use things like execution monitors, and we can come to strong conclusions about whether it's likely to stop in the next nanosecond. But if you go to write a proof for this, you're going to have a bad time. It's provably impossible, right? So this is provably impossible as well. One of my senses in that the recent days, there seems to be a belief that the LLMs can answer questions other computers can't answer. And in fact, they cannot do that because they're running on the same computers, right? So I cannot ask an LLM, hey, will this program ever finish running? No, the only thing it can do is run that program much less efficiently than the programming language. I taught an introductory Python class last year, and it was very interesting to see students put Python code into ChatGPT and ask ChatGPT to run it, which of course ChatGPT can do. And why would you do that, right? Because Python code on this computer runs very fast, right? And it gets faster every year. Python keeps getting faster, right? And ChatGPT, first of all, it's running over the internet, so even if it were a fast remote Python server, it would feel slow to me. And then it's not running a Python server, right? Okay, so here's the sketch for how we're going to build this out. We're going to start with finite automata. The motivation for starting with finite automata is you have to start somewhere. In the Turing machine, usually the way people describe it is, well, a Turing machine is a push-down automata with multiple tapes. And then you say, well, what's a push-down automata? And you say, well, a push-down automata is a finite automata with a stack. And then people say, what's a finite automata? And that's why we start here, right? So we're going to start with finite automata and build up. Do you have a question?
I didn't understand it. Can you repeat that?
Okay. So the Turing machine is the mathematically interesting model of computation in the sense it is arbitrarily powerful. Any question that can be answered by a computer, we can program a Turing machine to answer. Okay. So then that natural question is, well, what's a Turing machine? And usually the way Turing machines is described is like, well, you know what a push-down automata is, right? And you probably don't, right? Because I didn't remember what a push-down automata was until I was prepping these slides, right? So you say, well, a Turing machine is a push-down automata that can go forward and backwards on its input. And you're like, you got to define your terms here, right? I don't know what's going on. And it has a stack. And so then we say, well, what's a push-down automata? You say, what? Okay, it's a version of this thing called the finite automata, which is also called a finite state machine. You may have heard of finite state machines. Okay, so we start with finite state machines, right? So it's a finite state machine that has access to some memory, and it's not random access memory, it's stack-based memory. And then the Turing machine has random access memory. Right? So that's why we start with finite automata, because anywhere else is starting in the middle. You could argue finite automata is starting in the middle, but most people can handle finite automata pretty well. And regular expressions are the language that's equivalent to finite automata, and those aren't too bad either, right? So, what are we going to do? One other thing to take note of as well, there are some of these open problems. And one of the most interesting open problems to me, I do hardware security, is my perception is that outside of the field of computer science, the theory of computation stuff and the automata stuff is considered boring or old or complete or something, right? Maybe it was settled in the 50s with the creation of programming languages. But there's one fundamental problem we still can't answer, which is that no one knows how hard it is to factor numbers. And this seems like a very, very easy thing to do, right? I'm very, very good at dividing 19 by 6. I know exactly what that is, and I have many ways I can specify that. I can do that with reals, I can do that with rationals, I can do it with integers. That's no problem for me. I'm taking a cryptography course right now, and I put those slides together after writing this. I don't know if you've ever tried to divide a 4,096-bit integer by another 4,096-bit integer. Or they're not integers, they're ints, right, because they're finite length. It took weeks for me to work all of the bugs out of this code. And the reason I could work all of the bugs out of this code is I actually wrote a Python interface for my C interface. So I just used a version of this code someone else wrote to test mine. If I had to test it manually, I don't even know what I would have done, right? And it seems so simple. But as soon as your division gets bigger than it's actually implemented in electrical engineering, so the electrical engineers had to do something very hard with the 64-bit division, right? And you say, well, I'm going to put two 64-bit numbers next to each other and have a 128-bit number. It is ludicrously hard instantly. Going up to 4096 is not actually that much correspondingly harder than going past 1, right? And you compare this to integer, or int addition, where it's the same as normal but with a carry bit. But like when I was a child growing up learning to arithmetic, I was like, oh, plus, minus, times, divide, these are all just elementary operations. No, division is incalculably more challenging than the other ones. And you don't perceive that, and then you go to program a computer to do it, and you're like, this is so hard. I have to keep track of all this information. Not only do I have to keep track of how these numbers divide each other, I have to keep track of their most and least significant bits. Anyways, it becomes very difficult very quickly. And so the RSA cryptographic algorithm, which is now falling out of favor because of some of the hardware things Amber talked about, is based on the notion that factoring numbers is hard. Now, I just said a lot of things that suggest factoring numbers is hard, but I did not say a proof. The only thing we know for sure is that no one has yet found a way to do division easily. There could be a very, very easy way to do division. And intuitively, the fact that it seems like there should be an easy way does not help convince me that when I am bad at it, that's because there isn't a way to do division quickly, right? So there's this open question in computer science, as long as computer science has existed, which is that, is it easy or hard to factor numbers? Nobody knows. We can't write the proof. We don't know. So in this sense, these theoretical questions that were mostly, we think of being as in the 1930s, are relevant today. The entire global financial system relies on factoring being hard, and no one can prove it. And so that should lend some relevance to the things we're talking about. There's also a notion of just measuring how good code is. I usually think good code is fast and doesn't take up very much space on my solid-state drive, because I don't have hard drives anymore. But there are other ways to measure goodness, and perhaps we should think about that as well. I'm going to look at my watch and see what time it is. All right, the role of theory. Okay. So Amber gave the good example of the 2013 breakthrough, right, where someone took a graphics processing unit and used it to do something else. And in hindsight, right, I mean, the way people talk about it now, it's like, oh, of course the GPUs are just doing linear algebra and they're not doing graphics. I don't think anyone knew this at the time, right? I remember I was in my undergraduate after that came out, 2013 through 2015, and I was still being taught neural networks were a dead end. They would never be useful, right? A year later, all of my classes were about neural networks, right? It was this instant turnaround. It's certainly my impression that we should not assume that because there were two types of computing hardware in 2013, CPUs and GPUs, and it was found out we were using the wrong one for everything. That is a 100% miss. We should assume, additionally, that the GPUs are also still the wrong hardware, and that we're doing all the wrong computation on all of the wrong hardware we have, right? So we seem to be, my impression is, a lot of very smart people have worked very hard on a lot of these problems, and there's no real grounds to think we're anywhere even close to how you should use electrical engineering to solve the mathematical problems that are interesting, right? Is the brain a neural network? Probably not, right? But it does contain neurons. It can perhaps be modeled as a neural network, but it certainly doesn't do matrix multiplications. There's no real mechanism by which a biological process can implement a matrix multiplication that anyone's aware of that I know, right? And so if we asked even just a basic question like, can a computer think? We can't even define think, and we can't even really define computer unless we're just using the Turing machine definition. And a Turing machine almost certainly can't think. It can't recognize images, right? And then there's also this notion of creativity. I have been round and around with people that are not computer scientists who are convinced that ChatGPT is being creative. And I know that's not true because I know how ChatGPT works mathematically, which is that it predicts what I want it to say. And the way it predicts what I want it to say is by studying what every human has ever written and then guessing the most likely response to a question. And to me, that is the exact negation of creativity. But this raises other questions, which is that when humans say of each other, I like how creative you are, do they actually mean that that person is very good at guessing what they want to hear, right? When we say creative problem solving, do we just mean this person comes up with solutions that I wouldn't have come up with? Because in fact, ChatGPT can do that, but it can't create. There are very few examples, I think, of things that look like measurable creativity, but like running the neural networks on a GPU seems creative, right? No one else had thought to do that. And I don't think ChatGPT could guess that it's supposed to be running on some other form of hardware. That isn't a meaningful question to ask it because no one has ever had that idea. So if you're only trained on what humans do, you can't have that idea, right? Google has, Amber mentioned AlphaFold. I am much more interested in Alpha Proof, which is their library of machine-written proofs, which are written in, I believe, the Lean programming language, and this is a good example of open source collaboration. Lean being a programming language for writing proofs developed by Microsoft that is used by Google to run on Gemini, which is based on results by OpenAI, which is then owned by Microsoft, right? By the way, Amazon's not in here anywhere, which is always interesting. My students often ask me why I don't teach about Amazon. I was like, well, maybe they should do something, right? AlphaProof is very interesting because they threw a bunch of challenging mathematical proofs into ChatGPT, or Gemini probably, and it wrote Lean scripts that solved some of them. And this seemed very exciting to a lot of people, and I looked into it more, and I guess the result was it's about as well as like a beginning graduate level mathematician. And to me, I think as an educator immediately, oh, the beginning graduate people those are the first people that are starting to do things that are non-trivial. So it is completely unsurprising to me that $8 trillion computing company can create a computer that can do things that are trivial, right? And I think it's very exciting that it can do the things that are trivial, right? But this was, I think, presented perhaps in not the way I expected, which is they're like, computers can write proofs now. It's like, no, they can write proofs that someone else has already written.
Already.
Right.
They cannot create.
And that's very different, right? when it writes the first creative proof, and a lot of the first creative proofs also will be, they'll probably be niche or side proofs that the reason no human has written them is like no one cared to check or invest the time in it, right? It is a lot of work to write a proof, right? So like if we start getting proofs of things like Fermat and stuff like that, I will be justifiably impressed, right? But I think like this computer can pass an intro grad school seminar. It's like, yes, we know, we designed those to be accessible so that anyone can do them without necessarily knowing their background and training. Professor Sipser, who put this course material together, said, can we claim to understand computing without even understanding the factoring problem, which is, of course, much more simple than creativity. Like, is factoring hard is a much simpler question than what is creativity. And so his claim was that we do not understand computing, and I think I agree. I often use the term computing to refer to taking numerical calculations, and I do not use it to say image classification. It so happens that there is a way of writing an image classifier where it simply is numerical. Is that thinking? No, to me it ceased to be thinking once it became purely numerical, and then it was simply computation, right? On the left-hand side of the screen here, we have our first deterministic finite automata. I'm going to press this a few times. So what do we have here? Free your mind from thinking necessarily about computers. Place yourself in 1930s and think about what types of systems they're working with. And I think they're used to things like gears and pulleys and widgets. They're probably familiar with the abacus, right? So they're not thinking about random access memory. They're not thinking about processors and instructions, right? They're thinking about something else. So what are the things we start with? Well, this is a graph. It is a graph with edge and node labels. And it is slightly different from a graph in that there is one edge that comes from nowhere. And there is at least one node that is distinct from the other nodes. We can express all of this in set theory. But initially what we look at here is we take things and we call them states. The states map to nodes. We have states Q1, Q2, and Q3. It is quite common in theory of computation, because this came out of the school of mathematics where 0 was not a natural number. They very frequently 1 index instead of 0 index. You'll see me going back and forth. So Q1, Q2, and Q3. And what we'll see sometimes is actually there will be a state labeled Q1 that is also labeled Q0, which is to note that it is the initial state and also the first state, which is interesting, right? So we have transitions, which are edges in a graph which have labels. And the labels here are labeled with sets. And those sets are the combination of labels. So many of them have a unary label, 0, 1, 1, 0, 1, 1, 0, 0, 1, right? And they do include self loops, right? There are cycles permitted in this graph. This is not an acyclic graph. It is, it is directed, right? So these edges are directed. What does this correspond to? Let's take one more, and this is going to give us the start state. So we specify where we begin in our graph. And from that, you should begin to think about what we're actually going to do with this. It's like, this is a graph that begins. So there's going to be some notion of chronology or progression. Something is going to move through this graph similar to max flow. These two states are special. This one has the special incoming edge. We don't have to think of that as an edge. We usually denote it graphically as an edge. It makes no difference. What we're going to do is I'm going to create a tuple, and I'm going to list Q1 specifically in it, and that's what's going to make it special. Q3 is the same. Q3 is not necessarily an individual. When we talk about acceptance states, usually it's a set of acceptance states. I have a unary set here. So what happens? We're going to start here, and we might end here. And whether or not we end here determines on what transitions are followed through the graph. So we have to determine what causes those transitions to progress through the graph. So how are we going to do this? Well, we're going to take some input. That input, I'm going to say here finite bit string. We do not care if it is a bit string at all. We can accept any form of information. It so happens that after all of this was put together, Claude Shannon came in and proved we can put every bit of information inside a bit string. And then a short while after that, they found out they couldn't put the real numbers in the bit string, so that was a little bit dramatic. But we're we're going to accept any finite bit string. It is important it's finite. It cannot work with infinite. This is a finite automata. Yes. And so we're just going to represent that as the set of two symbols.
Two symbols.
Those are not numbers right now, those are symbols.
Okay.
They go back and forth, right? So we can use these symbols to represent numbers, but we can also use them to represent other things. And one of the other things we can use them to represent is a finite automata, right? So we have two symbols, we take them to the nth power. So 0, 1, 0, 1, 1, 1, 0, 0. All of these are finite bit strings. Yes, you know what finite bit strings are. That is the input. I like to think about things in terms of function types. Not everyone does. The output is quite simple. It is either a Boolean or a bit. I have completely given up differentiating Booleans and bits. It makes no difference to me at all in my life anymore. So we're going to get either a 0 or 1 back. We often will also say accept or reject. You begin in start. So you read a symbol. And now where are you reading those symbols from? You're reading them from the finite bit string. So you start in position 0 or 1, the initial position of the bit string. And separately from having this notion of a bit string, somewhere else we have the notion of the graph in the automata, right? And so at every symbol or letter or digit or character of the bit string, we progress to some new state in the automata. And perhaps it's the same state or perhaps it's a different state. And we progress through these states as we progress through the bit string. And when we're done, we will either be in an accept state or not, and we will either accept or not based on whether or not we're in an accept state, and that it produces our 0, 1 output. And that is the model of computation. Let's look at an example. So I'm going to use a combination of features here. It is common to represent the inputs to these automata as literal strings, like you just write them down. I am going to do that at every point in the class after this initial one. But I'm going to begin initially by using a Python list. Why do I want to do this? To me, there is a difference between the input to a finite automata and the sort of linguistic or programming notion of string. And I'm going to demonstrate that by using a different collection type to store the same data. In Python, as you know, if I write an iterator for loop over either a list of single characters or a string, I get the same results.
Yes.
There's no information theoretic difference. I want to show that there is a potential difference. And okay, so what are we going to look at here? I'm going to demonstrate the process of reading some string. I'm not going to show you the string. I'm going to generate the string as we read through it. So the first thing we're going to do for all strings, for any possible string, or any possible input, which is a bit string, is we're going to begin conceptually in the start state Q1. Q1 is denoted with this incoming edge that comes from no other node. So before I look at a single letter of my string or a single digit of my binary number or a single symbol on my tape or any other notion of abstract input, I will consider myself to be processing or holding internally in computer memory, for example, the notion of Q1. I take Q1 and I see a 0. 0 being the first element of our bit string or the first input or whatever have you. And so, because I was currently in state Q0 or Q1, and I see the symbol 0, I inspect Q0 for outgoing edges. I examine the labels of those outgoing edges, and the label for which matches the input string, I will follow that edge. In this case, I have an edge labeled 0 that is a self loop. So when I perceive a 0 at the beginning of the string, and I began in position Q1, I will loop back to Q1. So there's a variety of ways to stylize this, but if I see a Q1 and then I see a 0, I return to Q1. Q1, the initial state. I'm using Q to denote the states here. Let's continue. I believe this will make more sense as we go on, and we will stop when we get through the string and see if you have any questions. Okay. So I find the label containing 0 that is outgoing, a directed outward edge from Q1. Let's look at a 1. So after completing our self loop to Q1, because we perceived a 0, we perceive a 1. We are currently still in state Q1, so now we perceive the numerical value. Well, now we see a 1. We saw a 0 already.
Okay.
And now we see a 1, the next letter. So Python list 0, 1 and string 0, 1. I was in position Q1 at the end of the first one, right? So I have a self loop back to Q1, so my current state is still Q1. When I see Q1, or when I'm in Q1 and I see the numerical value 1, I inspect Q1 for outgoing edges. There are 2 outgoing edges, one labeled 0 and one labeled 1. The outgoing edge labeled 1 is a directed edge from Q1 to Q2. So the presence of that 1 forces my computation along the labeled edge, which means that my current state becomes Q2 after the presence of the 1. If I see an additional 1, I began in state Q2. So now, from Q2, I'll inspect the outgoing edges. There are 2 such outgoing edges. There is a 0 labeled edge to Q1 and a 1 labeled edge to Q3. Since I read a 1 at this time, I take the 1 labeled edge to Q3, and so my current state becomes Q3. You got it. I see you understanding. Good job. Let's keep going. Oh yeah, what's your question?
No, I was going to ask for 0, 1, 1.
0, 1, 1?
0, 1, 1, 0, yeah, 0, 1, 0, 1.
0, 1, 0, 1. Let's do it real quick. Okay, so you said 0, 1, 0, 1.
Yes.
Start here.
Okay.
0.
Q1, 0.
And you said 0, 1, 0, 1?
0, 1, yes, comma 0.
0, 1, 0,
Go back, 0.
1, ending Q2.
Q2. Okay.
Not accepted, right? Still in Q2. Does not make it to Q3, which is the double circle accept state.
Okay, so it has to be.
What happens if we get a 0 after we see 0, 1, 1? Well, we have a self loop labeled with all the possible elements of our set, so we just stay in Q3 no matter what we see after we see the second consecutive 1.
0, Q1.
Okay, which 0, 1?
Okay, so if 0, it's in Q1, right?
Not necessarily.
Not that.
If I am currently in Q1 and I see a 0, I stay in Q1.
Stay in Q1.
If I'm currently in Q2 and I see a 0, I return to Q1.
Return to Q1.
And if I'm currently in Q3 and I see a 0, I stay in Q3.
Q3. Okay, so now in this stage we will stay in Q3.
Yes, there's no way to get out of Q3 unless we see something that's not a 0 or 1.
So it's a loop.
Yes. That is a trap state. That is an infinite loop, right? Okay. Find a label containing 1 out of Q3. We did. So, what do we say here? For 0, 1, 1, 0, 1, we took our automata, we followed all of the edges, and we looked at the current state, and we looked at the current letter or character or digit, and we figured out what the new state was. We did that 5 such times, and at the end of that we noted we were in position Q3 or state Q3, and we noted that Q3 is labeled the accept state by the presence of the double circles. So what does this mean? 0, 1, 1, 0, 1 is accepted by this automata. This automata returns 1 or true or accept or positive or a non-error case in the event it is furnished with the string 0, 1, 1, 0, 1. So what we have is we have a computer that says yes to that string and also to some other strings. I denote that by using the Python notion of assert, where it is true that M1, which is the name of this machine, 0, 1, 1, 0, 1 is true. M1 accepts by ending in Q3. If there were not, so I think you gave the example of 0, 1, 0, 1.
So this one will end up in Q1 or it is supposed to end up in Q2, right? Or Q3? With 0, Q1.
To return accept, to return true, we must end in Q3. There's not necessarily a notion of supposed to. There's not good or bad outcomes. There is just computation. It just returns 0 or 1. It is a mapping from bit strings to bits. This bit string maps to the bit 1. The bit string 0, 1, 0, 1 maps to the bit 0.
0. Okay.
Because it does not go to 3. The function from bit strings to bits. Not to worry, we have an exercise for you. Do you want to use the board?
No, false.
What is the sequence of states that it progresses through?
Q1, Q2. Q1, it will stay
Stays in
Q1,
Q1, then it goes to Q2.
Q2,
Yeah,
then back to Q1,
and back to Q1.
and then back to Q2.
Then back to
so
Q2.
It doesn't end up in Q3.
It
so-
doesn't end up in Q3, so it returns to 0. Very good. When you are thinking about that, well, I'll tell you what I think, which is that this feels a lot like recursion and a lot like for loops and a lot like if statements to me. Okay. Very good. So let's introduce some terminology. The automata themselves aren't particularly interesting. It's proving properties over them that becomes quite interesting quite quickly, and also proving equivalence between them in languages. So what are we going to say? We're going to say A is the language of M1. What does that mean? Well, it means that every bit string for which the machine returns 1, that set of strings constitutes the language of that machine. The machine does not produce a language, but it accepts a language or recognizes a language, right? So 0, 1, 1, 0, 1 was part of the language of M1, and 0, 0, 1, 0, 1 was not part of the language of M1. Because to be part of the language, you have to cause the machine to direct to an accept state. An example of when we might care about languages a lot is, well, can we make one of these things that represents having a prime number of 1s followed by a 0? That gets pretty hard pretty quickly, right? Because now we're asking you to do division and factoring, and we don't actually know how hard that is. Yeah. But that's an example where this becomes very interesting. So, right, if someone were to demonstrate that you could write the deterministic finite automata that tells you if you have a prime number of 1s, that would be very, very exciting, right? We're going to frequently use this notation that A is a language, which represents the language that is recognized by M1 or any other M, right? Here is I think our first formula of the term. We take letters, I think that's lowercase omega, or no, sorry, we take words. So a word is an element of the language. So what is a word? A word is a bit string, and a language is a set of bit strings, or a set of sequences of bits, right? So W, I'm going to call it W. If a word is in the language, that implies that there exists some I, and that I has to be less than the length of the word, such that Wi and Wi plus 1 are both equal to 1. And that precisely corresponds to our automata that needs to have the 2 1s in a row to get to Q3. Does that make sense? How this is a logical way of writing out the same operation as the automata we just had?
No, actually. Can you elaborately explain it?
Yes, right. So to me, this makes a lot of sense. There exists some I. That I is a bit in the bit string of some length.
Okay.
In the case of 0, 1, 1, 0, that is going to be 1, because I am going to see 2 1s in a row beginning from position 1. But there is somewhere in the bit string that is not right at the end.
It's not right.
And when I look at the ith letter of that bit string, I'm going to see a 1. And that is going to conduct me from Q1 to Q2. And then when I see another 1, immediately, it has to be immediately in the next position, because if there's a 0 there, it doesn't work, right?
Yes.
So this conducts me from Q1 to Q2. This conducts me from Q2 to Q3. And then I'm done. I don't care what happens in any other places in the string, right?
So it end up over there.
Yes. And then we'd want to be a little careful, because you'd say, what happens if you're already in Q2, and then you see 2 1s in a row. In this case, we don't care about that, because that can't, right? If we're already there, there's already 1, right?
End up in Q3.
Yes, but it's very easy to imagine there might be something we're trying to compute where we have to express something more complicated than just there has to be 2 1s next to each other, right? So our automata is more powerful than this form of statement, but this statement is equivalent. Okay. So we can just simply say in Python, and this is absolutely illegal in terms of an automata, we cannot ask an automata, hey, does your bit string contain this substring? No, you have to write the program that does that, right? But Python has run that program. And so we can say our automata is equivalent to 1, 1 in W. Let's do the formal definition. Let me look at my watch. Okay. So that's listed from Wikipedia. Wikipedia is absolutely correct. There's no reason to argue with them. This might even be a link. Nope, it's not. Finite automata, finite state machine. We recognize patterns in a sequence of symbols. I think of it as we recognize bit strings. Bit strings contain patterns. Ooh, what happened to my font there? Look how small that is. That's cute. I only say finite automata when I'm teaching theory of computation. But I do only say that. To me, it is quite relevant to finite automata, specifically when I'm talking about theory of computation. Most of the rest of the time when I'm doing things that look a lot like a finite automata, I do say state machine. So a traffic light, I would say that's a state machine. I would not say that's a deterministic finite automata, though in fact it is both, right? But when I'm doing systems thinking, when I'm doing engineering, when I'm building a spaceship, right, I say state machine. Everyone knows what that means, right? I think the engineers are taught what state machines are, and only computer scientists know about finite automata, right? I'm using the notion star FA. There is more than one kind of finite automata. In fact, there's 3 we're going to look at in this class. So many of the things I'm telling you right now are true of any finite automata, even though we are specifically dealing with deterministic finite automata at this time. Okay. So this is going to be the definition of the deterministic finite automata. It is a 5-tuple. I say tuple for that. Some people say tuple. So I'm going to say 5-tuple. Yeah. Wait, do I say tuple or tuple? I try not to say 2 in it unless it is a pair. So 5-tuple.
You say tuple.
I meant to say tuple, and then you corrected me, so I think it's tuple. We're going to say tuple.
Tuple, yeah.
We're going to say tuple. It rhymes with couple. Okay, 5 things. Q, a finite non-empty set of states. For us, originally that was Q1, Q2, Q3, no problem. How many states can we have?
2.
Any finite number.
Oh.
We started with 3, remember? Q1, Q2,
Q1,
3.
yeah.
That was funny, right? So the states, the number of states does not have to correspond to the number of characters, the number of symbols. All these things are independent. They just all have to be finite. Okay. I have a finite number of states. My computer also has a finite number of states, right? So that's finite memory.
Q1, Q2, Q3, are we considering them as a state or the characters?
They are states. They have no correspondence to characters at all.
So, but that is a definite, like?
A state is an abstract model of computation. A character is something we can observe. Where the characters show up on the deterministic finite automata is they are labels for edges of a directed graph.
So, I'm saying characters can be infinite, right? But the states cannot be infinite.
None of them can be infinite. For these models, we have to have a finite number of finite characters. Yeah,
Okay.
yeah. And there do exist infinite models, but we're doing finite only. These things turn into something called Bushi automata, B-U with 2 I's on it. And they look identical, but there's just a little bit of additional proof you have to do to handle infinite things. And it's not too bad, but it is out of scope. And it's out of scope for a very good reason. When I learned this class from the person that I actually know Amber Huffman for, I didn't realize that, but like Lars Bergstrom or something, he runs Android at Google, said the difference between finite and infinite versus like some other decisions we made is there's a lot of hot new startups coming out of Silicon Valley that have like a faster computer or a faster memory or a computer that can do some like new form of arithmetic. but there's no hot new startups coming out of Silicon Valley that have infinite memory. No one will ever solve that problem. So there's things we can play sort of fast and loose with. We can say, oh, you can have as many symbols as you want if they're finite. You always can have any finite number of anything, because we're sure the engineers can deal with the finite problem. As soon as you ask for infinity of something, we say, no, that's completely impossible, right? And so, and this is even just the difference between like any countable number pretty much is fine sometimes, right? Okay, we have a finite non-empty set of input symbols called the alphabet. I think I will usually remember to call this the alphabet. Why is this called the alphabet? This was lifted directly from linguistics. The linguists had all this stuff before the mathematicians. So when I said string instead of number, well, a bit string, that is just a number. Why do we call it a bit string? Because that's what the linguists called it. Yeah. So we're going to have a non-empty set of input symbols. We're going to, generally speaking, use zeros and ones. But oftentimes we'll say, like, put a symbol that means this. And we can do that, because we can do that any finite number of times. If we agree upon the meaning with each other, that is legal. Delta is the transition function. It is a mapping. What is it a mapping from? So when we were progressing through our finite automata, what did we do? We looked at the input symbol and we looked at our current state. So delta is a function that takes an input symbol and the current state and produces the new state. When I'm in Q1 and I see a 0, I return a Q1. Yeah. And so that is, right? This is a set. This is a set. That is lowercase sigma, so that's an element of sigma, right? That is a set. So what is this? This is a cross product of two sets that maps to a set. How do we represent that? Well, this thing is just a set of tuples. We have Q0, the initial state, and Q0 has to be part of Q. This is a typo. That should be script Q. These should be the same Q. I tried to fix all my typos last night. I didn't get all of them. And then the last thing we have is the accepting state. Here's another typo. My dot is colliding. There is one initial state, because you have to start in one fixed initial position. There can be arbitrary many accepting states. It is in fact possible to list every single state as accepting. That simply means that you accept every string in your language as the universal language, right? It is also possible to have an empty set of accepting states and accept no language. Or, well, no, you do accept a language, you accept the empty language, you accept the language that contains no strings, right? Your accepted language is the empty set. So we can't accept the universal and empty set. Usually it is only mathematically interesting if there's an accepting set that accepts something that is interesting, like this string contains 2 ones, or this string contains a prime number of ones. Does that make sense?
And how does the empty states work,
Yeah, so it's completely reasonable to say, I am writing a program, and the program is return false. That's allowed. And that is the program that over any input, no matter what, returns false, right?
It will return false.
Yes, and that's the same thing as having no accept states.
Okay.
And it is not particularly interesting, but it's possible. And it's important that it's possible, because sometimes you'll just be like, I just need a computer that can return something real quick, you know, for proof.
It doesn't have to be.
Yeah, and you can do the same thing with the return true, right? But is it Python 3 or Python on Windows?
Python 3.10.
Oh, I haven't updated it. Don't look at how old my Python version is. We can create a we'll call this mn, and it can accept actually any number of arguments, right? So I can actually accept some x, right? Is it capital false in Python?
Yes.
And so no matter what my string is, I can return false. That just means there's no accept states, right?
Yes.
And then the other example we had earlier is given mn, and that's completely reasonable, and that's completely reasonable as well. So we can either have computation or not have computation inside of our deterministic finite automata. And the way we represent whether there's computation or not is by how many accept states we have. And an accept state essentially corresponds to a return statement that says return true, and everything else says return false. Okay. Let's explain this. I very, very strongly think of the states of the internal automata as the values of program memory. This is new. The original automata theorists did not think of this way. They didn't have the notion of random access memory, right? I do. To me, my computer is just holding one very specific, very large integer at all times, and that is the name of the current state, right? And so the early models of computers, justifiably, they thought of this as having a small number of finite states because they had 4 bits of memory, which just means they all had 16 states, right? That wasn't that hard to deal with, right? Now we have, comically large numbers of states, right? I couldn't even calculate how many digits the number of states has, right? So, but I do think of this as the internal configurations of computer memory. And in fact, there's still many memory constrained applications, right? I have a good colleague that works for Amazon, and in his telling of it, I think he writes Lambda functions in Scala and Rust. And he likes Rust a little bit better because when he writes functions in Scala, sometimes he doesn't write the most efficient function. And if he writes a function that uses too much memory in the Java virtual machine, the engineering team calls his desk and tells him he has to write a more efficient function. And that's pretty interesting, right? So like his job all day, and he does automated reasoning. So he's writing programs about automata and has to be thinking about how many states he uses when he's thinking about the automata, right? Like a very interesting job and a very interesting career, right? Yeah. Possible inputs. To me, that's always binary, and if we're not using binary, we will use something that we can convince ourselves is binary. Transition function. I think that we said all of this out loud. Here's our example. Okay. I've only changed a few things here, but you'll note that versus the original example, when I introduced the tuple, I said, I have a Q0. Well, the name of Q0 in my state is Q1. This is the 0, 1 counting thing. My initial state was named Q1 in the machine I showed you. And my accepting state was only Q3, so this is a set with one element. So I've concretized these two things, and now we're going to concretize these 3 other ones. Now you know what Q is going to be. Q is the set of states. Yeah, so that's going to be this with Q1 and Q2 in it, right? And what's big sigma going to be? 0, 1. That's all we're reading. Delta is so annoying to write out. I have a table. If I am currently in state Q1 and I perceive a 0, I remain in Q1. If I am currently in Q1 and I perceive a 1, I proceed to Q2. The same. The same, right? This is a self-loop, right? Yeah. And you'll notice that what I have done now is I have gotten very, very close to expressing a programming language using nothing but set theory, which is potentially useful, right? I expressed this in Python, and in fact, you can print that out. Do we need to spend time with this? How do you feel about that? You see what I'm doing here?
Yeah, we
Let's do it. Okay. So, we imagine, let's see, this thing is named M1, and its second element is the delta function, right? What does this mean? Well, this means that if I am in state Q1 and I see a 0, I will be directed to state Q1, and if I see a 1, I will be directed to state Q2. And what else does this mean? I'm glad you asked. This is a little bit easier if we do, I'm going to create an alias for delta. That's delta. So I can say delta of Q1 of 1 and that gives me Q2. We can loop. What's going on here? Q1 is a state. Delta of Q1 is a list of edges. Delta of Q1, 1 is the edge that corresponds to this character.
Q2.
And that edge corresponds to a new state. Because I know what the starting edge is. That's the edge from Q1 to Q2, right? So dQ1, 1 means that when I receive a 1 from state Q1, I return a new state. So this has some return value. Or it's not a return value, this evaluates to some value. That's the proper way to say it, right? Because this is not a function, this is a dictionary.
So value for state.
Yes. So this thing, that, whatever, that thing is a state, right? So I plug that state back into delta and get a new output. And this can be quite fun because you can just keep stacking these things and you essentially can just build the string at the end. The only difference is you have to make sure you get these two brackets, and that's just syntax, that doesn't matter, right? But for example, if there's not two 1s in a row, then I don't get an accept state. But no matter what I do here, if I put two 1s in a row anywhere, I will always get an accept. And if they're not in a row, then I don't get it. And so I think the other thing that's non-trivial to demonstrate is this one. So that's what the automata is doing. And we can implement it with dictionaries. And it would be more natural to implement it with lambda functions, right? But it is just fine with dictionaries. You can even do something like D equals lambda Q. I will call it, what should I use for sigma? I'm going to call it A, which denotes a letter. And that is M1. D is in the, delta is the second position because I have Q0, or the set of states is in the 0th position of my tuple. The set of letters is in the 1th position of my tuple, and so the delta transition function is in the 2th position of my tuple. And then this is much easier to write a for loop over, so I can set my initial state, so we'll say Q equals Q1. And then I think what I can do is I can even just write a list comprehension where Q is set equal to the new delta value of the Q value and some input value for A in, oh, that didn't quite work. Ah! That is the character 0 instead of the numerical value 0. There you have it. And then we can see that we are in an accept state at the end. Starting Q0. Or starting Q1. So we start in Q1. We read a 0, we go to Q2. We read a 1, we go to Q3. We read a 0, we stay in Q3, we read a 1. I'm going to keep defining terms. A string is a sequence of letters. This is a sequence of letters because my letters are numbers. This is closer to the automata theory version of a string than this thing was. because those are ASCII characters, and that doesn't make sense mathematically. It makes sense mathematically to have an ordered collection of numerical values, and we think of that as a string. And in fact, in the C programming language, a string is just a character array. Yeah. The language is a set of strings, as we've discussed, which is a set of sequences of letters. The empty string is of 0 length. We sometimes denote that big sigma to the 0, and we sometimes denote this. I will sometimes use lowercase sigma here, and I will try and point that out whenever I do it. Because sometimes I use lowercase sigma to refer to any letter, and sometimes I refer to the empty language is the empty set, which I use. That is LaTeX var nothing. Right, this is important to point out. The empty string is not part of the empty language. The empty language is the null set, is the set of size 0. That means it contains no elements. The empty string can be part of any language, but it cannot be part of the empty language because there's no strings that are part of the empty language, and it is a string. They're both empty. One of them contains no characters, and is therefore a string of length 0. One of them contains no strings, and is therefore a language of size 0. We say M accepts string W for word. Why is it a word? It's an ordered collection of letters. Right? If there is a sequence of characters such that, and this is what I just showed you right here. This is the same Python. I'm going to save this. Or am I going to save it? No one except me is going to use this Discord, but I'm going to use it. Oh, and I need to grab the lambda as well. That's not too bad. I'm going to grab all of this. Okay. For all for all letters in the word, W sub I is the ith letter of the word. All of those letters must be in big sigma. And there must exist some sequence of, what are those R's? Those R's are going to denote states. There must be some sequence of R's such that R0 is the 0th state, and R of the nth state, the final state, is an element of the accepting state, right? So that's our beginning and ending condition. We can think of that as input and return. And for all letters in the string, we have a transition function that transmits us from the current state to the novel state by observing that input letter. That is all. That just means that there's an edge in delta or in your graph, however you want to think of it, for every single letter in the word. And that's our stretch break. We are 15 minutes behind, and that's okay because we can go any speed we want.
Yeah.
So, do you want to stretch?
Yeah, it's fine.
Okay, well, I'm going to go get some water. And you can look at regular expressions until I get back. Do you have a way to get to that Discord? I've sent you an invite to it in a variety of ways, but it's on the bright space. Stream is healthy. Stream is healthy. All right, ready? All right. Heard of regex?
Regex, yes.
Yeah, so apparently it was based on this idea, and they're not actually equivalent. I don't know regex that well. For some reason, I never ended up using it. Seems quite powerful, right? Yeah, so, whoops. I also never learned SQL. I don't know. There's just there's stuff that if you don't learn it and then you know how to solve the problems without it, you're like, what do people use that for? It's like, I know how to write to the file system. So anyways, regular operations. I've heard it is commonly confusing for people learning programming, or no, for people learning theoretical computer science who already know programming, for me to call these things regular expressions. So just be aware it's a technical term. I try and say regular expression instead of regex and not go back and forth between those two. And I think I've always successfully written this down. Even if I abbreviate it, I say regex with a P at the end, so you know it's the regular expressions. Yeah. Let's look at some examples of how we are going to build languages using regular expressions which are not regex. One way to do this is we're essentially going to take operators. And we're going to begin with operators because we've sort of already talked about strings a little bit, and so I'm going to just trust you to be able to think about strings. We will define them formally when the time comes. And so regular expressions are generated by regular operators. Regular operators apply to languages. A language is a set of strings. Okay. One legal regular operation is union. It is identical to set union. This is not too complicated. I think you know what this is going to show before I show it. Oh, look, it's everything that is in both of them. No problem. That's a set. This is a way to create a language, right? Strings which are of length less than 4 and contain only 0 or 1 can be expressed in this manner. We can enumerate them and then take the union. Okay. Concatenation is another way to create languages. And this is where the language theory to me gets quite interesting, because I usually think of concatenation and union as the same thing, right? If I concatenate a list together, that's the same thing as taking the union of a set that contains those elements. It's just you lose the ordering. It is a big deal for languages that there's different ways to combine these things, right? Because you can say, oh, I have language A and D, and I combine them. And does that mean you take all of the things that are in both language, or does it mean you take everything in language A followed by everything in language B? And those both make sense, right? So this is concatenation. It's string concatenation. It's not too exciting. In Python, it's not too bad. You can do addition, right? So this is the set of everything with 0 or 1 zeros or 1s, right? Or no, with 1 or 2 zeros or 1s, I should say. 1 or 2, 0 and 1 each. And then we also make sure we specify that A always comes first, right? So concatenation, not too bad. Same with string concatenation, right? Star is so much harder. It is incredible how much harder star is. This is often called, I think, the Kleene star, after some famous logician named Kleene. Yeah, K-L-E-E-N-E. As far as I can tell, there were just like 30 people in Europe in the 30s through 50s, and everything's named after them. And I don't know that they're any smarter than the rest of us, but they decided to name everything after themselves, right? So what is this? Well, when we apply star to a language, we take arbitrary repeats of that language. What's the problem with this? This one's infinite. I didn't cap the number of repeats. That could be a slight problem, right? And the first time it's a slight problem, it is very difficult to print an infinite number of strings in Python. So what have I done? I've gone to iter tools and I've included count. This is the sequence of natural numbers. I don't remember if it starts with 1 or 0, but you can tell which one. And it doesn't affect me here at all, because I'm not using numeric file. And so what do we say? We take A, times n for a in a for n in count. And then I'm going to take 3 nexts, because I can't see this whole thing, right? This is a lazy evaluated generator. So this does contain an infinite number of values, but they're not all computed at once. Not too bad. Strings which contain 0 or more strings in a. There do exist languages that handle infinity quite well. Haskell, famously, standard amount. I could have written this in Lisp much more easily than I could have written it in Python, right? But you can handle it in Python, no problem.
Yes.
Okay, you get, it's an exercise. It's time for you to do something. Okay. There you go. I accidentally showed you the answer, so be advised it's on the next slide if you're following along with the slides. So go ahead and write this Python generator expression. I should have gotten you here before I took my drinking break. I'm going to go take another drinking break. Let me give you, do you need 5 minutes for this?
Yes, it should be on.
Okay. Oh gosh. to see what you're working with here. Do you want to see the answer? Or do you want to keep working on it? It requires one leap of
I think it
intuition.
should be 0. 1 0.
I used a join. I use combinations without replacement. Of course, you can write your own combinations without replacement, right? You know how to do that.
Yeah.
So what you do, you take a set, you generate a random number, pull things out of it one at a time, right? And then you can also just write an iterator that pulls everything, right? It doesn't matter.
It doesn't matter.
So S for n in count. What's that mean? So infinite number of S's.
Infinite number.
Yes. And that,
Join.
what do we do? That is for S. In join, so we join to nothing. Start with the empty string. That's fine, it's star, right?
Yeah.
We should be joining to the empty string. Join S. Combinations without replacement of A. How many 6 combinations? N. This N goes to there. Play around with this, and then what's this do? This essentially generates strings without adjacent ones.
Oh, okay. 1 0 0.
And I think we can show more than one of these, right? There's more to life than understanding iter tools, but it's quite useful for this particular set of things. So we can say, and you'll see there's never any consecutive ones. Oh, and I redefined it, so I'd have to start over. Wow. I do not like typing. Okay. So none of this is particularly interesting, but there's some things to look at. So I generated 100 of these, and that thing is still quite short, right? I don't know, is that 25 characters? And then there's never any consecutive ones. All of these, every single one is separated by some zeros.
Now 0. Okay.
And you might say, but they all end with large numbers of zeros. And yeah, but that's just how I wrote it, right? Like, that string is in here somewhere. We'll get there eventually. So you can take off any of the leading zeros except for the final one, right? Or any trailing zeros. Because this thing is part of the language, but this thing isn't. All right. I wrote the automata previously for a previous language. I think it's fine to call it the one that has to have 2 consecutive ones in it, right? Remember that? Q1, Q0. We did the dictionaries over it. This is it for this one. I'm not going to make you write it. So what's going on here? Not too bad at all. The only thing we have is there's no edge with a 1 coming out of Q2. So actually, the Q1, the 1 and 2 in Q1, the number of consecutive ones, you're not allowed to have 2 of them. So this is a very simple automata to write. Should we play? Do we need to play around with this? Let me pull it in and show you what's going on. Perhaps I did not select it. Okay. So how do we express this? The first thing we always do is we take d of some state. That's where I can go from some state.
Yes, Q1.
This is fine. Forget 1 I change. That's not allowed. That's 2 1s in a row. That's always not allowed. If we have an intervening 0, that's fine. And we're allowed to have 1s again after we have a 0. But we can never have more than 1 in a row. This will be allowed, and this won't. Easy. Okay. I'm going to look at the, there's a lot of exercises here. We have a closing exercise. We'll try and get there and try and catch up. Okay. One of the other things I would like you to know how to do is to draw the graphics. So I very pointedly have not yet asked you to pull out pen and paper and draw it at that automata. Because that automata was quite easy to understand if you drew it out, which you probably saw. You're like, hey, that's 2 nodes and 3 edges. I can draw that in 5 seconds, right? You can also draw it like this. This is the example of the original automata I showed you, which we know because it has Q3 and there's a self-loop of 0, 1 on Q3. This is the way I am going to represent automata, and all of my automata, if you look at the source code for my slides, are expressed this way, so you can learn how to write them as well. This is, I put some color. That's to match my slides. This doesn't matter. I create nodes that are circles. I have Q0. What's that? That's not a circle. That's the first edge coming in. This is a phantom state that does not exist. I'm using this to denote that my start state is Q1. So this is just a notational convenience, and that's why it's not a circle. Remember on my first one, I had like a dot with an arrow coming out of it going into the first state? This is the dot.
Okay, this is the edge, so edges.
Yep. What's this one? Okay. Q1 is as expected. These are called HTML style tags. I did that for italics. You don't have to do it. You can always just write QI. That's fine. No one will do that, right? So that is an italic Q with a subscript 1, italicized. It's a double circle. Why is it a double circle? Because we'd accept it there. That's fine. Q2 is the same, double circle. This is the phantom start edge. This doesn't matter. We don't care about that. Q1 goes to Q1 on 0. Q1 goes to Q2 if it sees a 1. And Q2 goes to Q1 if it sees a 0. Easy. That's all there is to it. Let's look at it visually. I think that makes a lot of sense.
Yes.
And in fact, I believe I made one mistake. I do not believe this is an accepting state because we never accepted if we ended on a 1. So so Q1 should be the only accepting state here. Can I do? Oh, I don't have LaTeX hooked up in here. Good. Regular expressions. Okay, what is a regular expression? Okay, we have the operators. What are we going to build these out of? Okay. We can apply the operators not just to languages that already exist, but we can create new languages out of nothing. The way we can create new languages out of nothing is with an alphabet. The alphabet being the sort of atomic components of a language, the individual letters. So we take sigma, the letters of the alphabet. The same sigma we use to denote the letters of the alphabet of a finite automata. And in fact, finite automata and regular expressions can look at the same letters, as we already demonstrated by building a finite automata, right? We can also use the empty set, which corresponds to the empty language. Say, we are going to take the intersection with nothing, or the union with nothing, or the star with nothing, or some combination there, right? And then we can also use sigma naught, the empty string. These are all legal things to build our languages out of. So those are our, I refer to them as atomics, indivisible. You can't get any smaller than that, right? They're all of length either 0 or 1, right? And then we're just going to put them together with union, concatenation, and star. And with this, we're going to be able to actually build essentially programs, right? Let's take a look. That's all bit strings. That's not too bad, right?
Yeah.
That's all one terminated bit strings. And that's a pretty easy automata to write as well, right? You just have an arrow going into an accepting state with a 1 on it, and then if you see anything other than a 1, you leave the accept state. So you always make sure the last thing was accept. That is the language we had previously. Anything, 2 1s, anything. All strings is 1 1. I always get a little sketched out. I defined a concatenation operation, right? I used a special like little circle symbol for it, which is a common concatenation operation. Basically, every proof I've ever seen, people don't write concatenation. They do the same thing that we do with algebra, where if you're multiplying 2 things together, you just put them adjacent. And I guess that's fine. But I want to point out, I broke my own rules here. This note is for. I should not write 1 1. I should write concatenation. I don't perceive there to be a reason to have any zeros in there, but I think there should be. Oh, it's so far back, but it's the concatenation symbol, which is like / concat in LaTeX or whatever, right? And everyone does this. They call it abusing notation often, but I say loosening the rigor of our notation because that's what it's doing. Okay, here's our goal. This is the sort of midterm goal for today. We'll end today with this and then introduce the next thing. We need to show that finite automata and regular expressions are equivalently expressive. And so how are we going to do that? Well, whenever we're doing equivalence, usually we're going to do subsets in 2 directions. We're going to show that every regular expression has some finite automata. We're going to show that every finite automata has some regular expression. And we'll say these 2 things are the same, and then that means once we prove something about one of them, we prove it about the other. So we're going to do this with closure. What are closures? I think of closure as being the description of a relation or an operation. I say an operation here, but a relation is fine. And a set. So we can say, is addition, or no, are the natural numbers closed under addition? They are, because if you add any 2 natural numbers together, if you take the addition relationship over any 2 natural numbers, the result is still within the natural numbers. This is not true of another operation, for example, subtraction. 5 and 7 are natural numbers. 7 minus 5 is not a natural number, so subtraction is not closed under the natural numbers. And this is how the integers were created. Said, oh, we have this operation for which they're not closed. So this is the example I always think of as closure. The rational numbers are not closed under quadratics. That's where the real numbers clone from. Remember, addition and division are much harder, which is why our machines are going to be just fine with the rational numbers and have a very, very hard time with the real numbers, because we don't necessarily have closure from our languages over division, right? What's the other one? Square root, right? So the reals aren't closed under square root. That's why you need the complex numbers, right? So many of these number systems come in. So we're going to take the notion of closures. We're not going to do closures over numbers. We're going to do closures over languages. And we're not going to do closures over addition and subtraction. Well, we kind of are with addition, because union is a little bit like addition, and concatenation is a little bit like addition, and star is a little bit like exponentiation. So it's not totally unrelated to arithmetic, but we're going to demonstrate those closure properties. I'm going to look at my watch. So we're going to begin with closure under union. This one's the easy one, so we're going to do it first. Just again, to be thinking about this, what's going on here? I have two languages, and I want to see if something is in either language. This is equivalent to basically logical OR in a programming language. I evaluate two functions and I return the OR of the return value. Remember, I can just do ORs because all of my functions are only returning 0, 1 so far. I only have accept, reject. So we're going to do closure under union. Okay. So we're going to take a set of language accepted by finite automata, or finite state machines. And we're going to see if it's closed. How are we going to do this? This is going to help us show that there's an equivalence between the finite automata and the regular languages. How are we going to do this? Well, let's take two machines. How have I denoted these machines? So they're over the same letters, because they're representing the same language, or what is going to be the same language, right? So that big sigma is essentially the language of the resulting language. So they can have their own sets of states, they can have their own delta operations, they can have their own starting states, and they can have their own accepting states. And it's unsurprising they have their own starting states and accepting states because they have their own states. So these, the 4 and 5 position of our tuple, our tuple, are both elements of the 1 position, and then delta is over those values as well. So essentially we're only changing the states, and this could cause changes to the relationship. So what we need is, given this M1 and M2, we need to show that there exists some M3 such that the language of M3 is equal to the union of the languages of M1 and the languages of M2. And it is not at all annoying to apply union to languages because they are sets of strings. So we can apply a simple set theoretic union there. We don't have to define anything. And this is the nicety of talking about languages of machines rather than machines themselves. Because what is the union of two machines? I don't know, because that's an ordered tuple, whatever. And taking unions of tuples is not something we want to mess around with. But taking unions of sets is no problem, so we can do that. So here is how we're going to think about this. We're going to see what state M1 and M2 would be in. And we're just going to create a machine that keeps track of the states in M1 and M2. It's just going to know both things. This is perhaps equivalent to parallel processing. This is perhaps equivalent to list comprehension. It's some way to calculate two things at once. And there's a variety of ways to do that, and we're going to introduce a relatively simple way here. So what is that simple way? Well, I'm going to define a set of finite states. And those sets of finite states are going to be pairs of states. So I'm going to take the cross product, that's supposed to say Q1, of course, I'm not taking Q2 itself. We're going to take all the states in M1, and we're going to take all the states in M2. We're going to take all of the pairs, and you should think immediately, that's polynomial complexity. And it is, right? This Q3 will have many times more states than M1 and M2. We take all the pairs, such that Q1, little q1 is in big Q1, and little q2 is in big Q2, right? And so these will just be the names of our states. We don't have to name a state Q sub 1. No one can make me do that. I can name my state the tuple Q1 comma Q2. I'm allowed to do that, right? All we said is that they're states. And because I can write this thing as the label on a node, on a graph, I'm not breaking any rules, right? Now we could renumber them, of course. We could say easily Q sub 1 comma 2. We could say whatever we want, right? The only thing that matters is that we have enough states to represent the cross product of all of the states of M1 and of M2. So how are we going to build this? We're going to build Q3. I'm so annoyed by that. Okay, let's see. I know. I have to put it in. let's see, the first argument of the cross product should be, I don't know if you can see it or feel it, but I have input lag on my keyboard. My computer's working so hard to screen cap. And there's not that many pixels there. It shouldn't be working that hard. Okay. Okay. So what am I going to do? Well, first I have to set my initial state of M3. Or not first. At some point I have to set my initial state of M3. So what do? No problem. I say the initial state is the pair of these initial states. Right? Easy. I'm essentially simulating M1 and M2 with a bigger, more powerful M3. Right? Delta is non-trivial. When you look at this, does it make sense to you? So what's going on here? Well, our states in M3 are pairs of states in the other M's, which means that our delta in M3 should look at a pair of states and a letter, and it should return a new pair of states. So that's what it does. It takes the pair of states, unpacks them, applies delta 1 and delta 2, uses the same letter, computes the new states with delta 1 and delta 2, and repacks them back into a pair of states. It's just packing and unpacking. This Python is very good at, right? That's just multiple assignment and tuple unpacking, right? So that's no problem at all in Python. Very hard in the early computers. But now when we see this, we'd be like, oh, that's why they put multiple assignment and unpacking in Python. It's this like very interesting computational technique that corresponds to all forms of branching computation, right? Okay. We don't want to play ourselves. The accept state is not, I have to be clear, it's not. It is not the cross product of the accepting states. Why is that? We're taking the union. We are not taking the intersection. We do not need both M1 and M2 to accept. Our list, or our string, only has to be accepted by either M1 or M2, which means that our accept state only has to be an accept state in either M1 or M2. And that cross product, that's both. That's requiring you to be accepted by both M1 and M2.
So
We need
it's not
something
required to be accepted by both states, right?
So say I have two machines. One of them accepts things with 2 1s in a row, and one of them accepts things with 2 0s in a row. And so I have let's define it. Ah! I almost got it. Okay. Let's define M2. These correspond to some, I don't know, languages, right? So the language of M1, I don't want to write the generator. I'm going to write some arbitrary bit strings, and then I'm going to filter it, okay? So we'll have some bit strings, which we'll call B's, and that's going to be, oh, there have to be strings too. That's so annoying. We'll do 0, 1, 0, 0, 0, 1. I gotta go in order, so I'm doing, and that's just for my thinking. Oh, and I said I had to go in order, and then I didn't. Okay. I'm not going to do every bit string of length 3. There's too many of them, right? Okay. And so then we can say LM1 is B for B in B's if M1 of B. So those are things that contain two zeros. Those are things that contain two ones. Why did I do this? These are sets. Of course they're sets. L1, L2. Okay. One is not an LM1. 0, 0 is not an LM2. They are not accepted. The union only requires either of them to be accepted. So what do we need? M3 is essentially return. I can't type in text. It's the OR. It's the logical OR. The union corresponds to the logical OR. Which means only one of these things has to return accept. Which means I only have to successfully be in an accept state in one of my two machines. This is the accept state in one of the two machines. All of the pairs of states for which either the first state is an accepting in the first machine or the second state is accepting in the second machine, all of those are acceptable. Another way to express this is it is in fact a cross product. It is just the cross product of all states. Yeah. And then we take the union, and that's the same union we're doing elsewhere, right? I consider this a proof, so I've expressed this as a proof. This is theorem 1. This is our first theorem of this semester. And this is the theorem of closure of the regular languages under union. And that's the exact same thing we just showed. I prove this by creating the language of a new Turing machine. Or not a Turing machine, of a finite. There you have it. Ooh. This broke. These are both individual images. Well, you don't have to do that exercise then. Fix the cropping here. But I can show you what it's supposed to look like. This is regex. Oh, my poor computer's working so hard. It's trying to capture its screen. It's trying to run Python. It's trying to... it's called regex, but there it is. And I do just always want you to see the, well, I wish I had a stronger computer. Oh, there it is. This figure width is probably supposed to be like 300 pixels or something. Oh, it's really struggling. I checked to see if my computer was fast enough, and I think it was because it wasn't too hot. I think it's too hot right now, is my theory. It's hot to the touch, right here. I think power's coming in. Okay. Can I do this on the board? Well, the thing is, we basically already did this, right? So these are the representations of the two languages we've seen already.
Yes.
Yeah, and so how do you take the union of them? Well, you write them down next to each other. You overlap their start states. And then you accept either's finish state. Yeah, it's just not that complicated. This definitely should have been done rendering by now, so my computer's just completely cooked. And I was hoping... Oh, we can scroll over. There's a scroll bar. Oh, it's so sensitive. Okay. So that's one of them, right? And then this is the other one. And I'm saying we don't need to do that exercise now because it's not working. Stretch break. NFA is after this. And then is it lunchtime? What time is it? I don't know what time it is in this time zone.
11:30.
Okay. I'm going to get some water. I don't think this is ever going to finish running. I'm actually... Am I worried about this computer? What can I close? The problem is web browsers are expensive, and so is live streaming. So let's close this. Close that. Close this. All right. Taking a 3-minute break. You're welcome. Voice is going to last all day. So I joined the Discord. I got the noti on my phone while I was holding it. You can either use it or not. I would use it.
I want to try it because I never used it.
Do you use like Slack at work?
No, I didn't.
Okay. Seems like a lot of the US like software tech company things use either Slack or Discord. And I don't know exactly what they use it for, because everything I hear they use it for, I would use Git for, like version
Git,
control.
yeah.
Yeah. But I think like maybe it's like, hey, can you finish this by lunch? It's like, oh yeah, that is a DM. That's not, you wouldn't do a like Git issue for, hey, can you finish this by lunch?
It's like a message.
Yeah. All right. NFAs. Non-deterministic finite automata. Okay. So we've set our goal, and our goal is to show equivalence between regular languages, which are things composed of union, concatenation, and star, and are built out of letters, the empty set, and the empty string. We want to take those and we want to show that those are the same thing as the languages that are recognized, not generated, recognized, returned one from by deterministic finite automata, right? And it's a lot easier to do that with non-deterministic finite automata. So let's look at an example. So that's the special concatenation character I've been using for concatenation, which I wish everyone would use. And essentially the reason I don't use it is because no one else uses it either. But I think it is more clear than just putting things next to each other. One of the things you can imagine is I print numbers in hexadecimal from time to time, and usually they're prefixed with 0x. Realistically, 0x is not a 0 character followed by an x character. That is a compound character. We should view 0x as one symbol. It is the symbol that means everything after this is expressed in hexadecimal. And so what I would like to do is I would like 0x, when it is prefixing hexadecimal, to not have a concatenation between it, because it represents one symbol. And I would like it to have a concatenation between it if it is representing a 0 followed by an x. No one does this. That's fine. We're going to demonstrate closure under concatenation. So what does this mean? Well, we're going to have two machines, same as last time, same as always, right? And we're going to create, or we're going to hope that we can create a machine. So we're going to say there exists an M3 such that the language of M3 is equal to the language of M1 concatenated to the language of M2. And then here's the thing I don't like. Well, we can just smush those things together and we can say LM1, LM2, A1, A2. But this is making noise, and my computer's muted. That's odd. I don't really want to figure out how to mute that. Is my computer muted?
I think it's muted.
It sure looks muted, right? So that's what mute sounds like. Okay. A1, A2. You're probably thinking, that sounds trivial. It's not. I have a slide that says non-trivial here. I got you. Okay, so why is this non-trivial? Well, the obvious thing to do is do the same thing we did, more or less, with union, where we just sort of like smoosh them together in some way, right? Well, so the obvious thing to do is you take M1, because that's what we're going to start with, and then you just take all the accept states in M1, and you just take an arrow, an edge from those accept states in M1 to M2. And that doesn't work. Why doesn't that work? Well, we don't know when we should transition from M1 to M2. We have no idea. Let me give you an example. Suppose M1 requires 0 appearance, let's see, 0 appear in odd length substrings. Right, okay, so if there's ever a 0, there must be an odd number of zeros, right? That's M1. Easy to imagine. That's just the odd number recognizer. Simple. And M2 is a negation of that. It requires 0 to appear in even number substrings. Here's the problem. when you see a 0, how do you know if you're supposed to be checking if you're in an even or odd numbered substring? You don't know. You have no idea. There's no way to figure this out. Because, yes, at least once 0 must appear in an odd numbered substring, and at least once it must appear in an even numbered substring. And as soon as it appears in an even numbered substring once, it can never appear in an odd numbered substring again. But when you start that substring, you have no idea which one you're in, and those are completely different automata, right? So somehow we have to think about two things at the same time. And we are going to do that using a little trick called doing both things at the same time. We're going to use non-determinism. We're going to allow our automata to be in multiple possible states and accept if any one of its possible states is an accepting state. Oh, this broke too. Oh no, I'm so sad. Can I draw one of these? I specifically made sure I could draw these graphs without opening MS Paint, and then my computer melted. Okay, so these are all circles. Okay. I want an arrow. I don't have a graceful way to do an arrow. So what am I drawing here? I'm drawing automata. I'm going to draw a self loop. I'm going to do it again. Oh no! No, I'm not. Okay. 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 How am I going to label these things? Well, at the top we have our DFA. That's too small. That's not changing it. I love MS Paint. Okay.
22, I think. What is the log?
I feel like, can I do 28? I think I can do 40. I don't believe you. You said it was too large. Okay. And then we also have an NFA. Okay. The differences between these things are going to be, for me, the edge labels. So I have edges. I don't have these labeled yet. This thing's going to be Q1. Q2. Q2. I love that I like specifically learned a new tool so I didn't have to do this, and it's too computationally intensive. But somehow MS Paint is less computationally intensive. Okay, and then this is Q2. I never want to use a mouse. I've never voluntarily used a mouse in my life. Okay. So, one way to do this is we say, okay, if you see a 1, you go from Q1 to Q1, and if you see a 2, you go from, it's trying to get me, okay, you go from Q1 to Q2, and that's all. We'll just say all of these are accepting states, right? So this is just a deterministic finite automata. Oh, I should have put a 0 there, right?
0,
So
yeah.
we should use some good strings here. Okay.
I think it went 1. Instead of 0, you should have put 1.
Is this okay? Is that what you're suggesting?
No, I think yes, 1. And on Q1 it should be 0, I guess.
Doesn't matter. This is just a different language, right?
Okay, sorry.
It doesn't matter.
Doesn't matter.
Doesn't matter. We're just defining a different language. And now let's define an NFA. you can either have 0 or 1 and stay in Q1. And this should immediately spark problems for you, because this set is equal to big sigma. That is the universal set. That means no matter what you say, no matter what you see, you can stay in Q1. But I'm going to throw a wrench in the works here. I'm going to say, but if you see Q0, or if you see the string 0, then you can go to Q2. And let's sweeten the deal a little bit. Let's say we really want to get to Q2. Let's say it is the accepting state. I'm going to go bigger this time. So let's say you really want to get to the accepting state. So these are completely different languages, right? This is an arbitrary number of ones followed by a 0. This is an arbitrary number of characters followed by a 0. That's not necessarily super easy to handle, right? Now, you can make a DFA that accepts this same thing, but it's quite different. It has a self-loop here, right, with 0 on it. And it has a 1 that goes back here. So this is a much simpler way to express 0 terminated. Why do I care about 0 terminated? Well, this is C language strength. That's an null terminated string, right? And that's how strings are stored in system memory, right? So that's like a no kidding serious real application that actually matters, and it's very, very easy with non-determinism, right? Oh, it's on a transparent background. Look at that. I love paint. That's all I can say. Okay. So, what are the new features? In deterministic finite automata, the intersections of the labels must be the null set. I cannot have any letter in 2 outgoing labels from one state. That's what makes it deterministic. So if there's a set of outgoing edges from some state, and one of them has a label that with 0 in it, I cannot put 0 on any other label. I have to know exactly where I'm going if I see a 0. That is what makes it deterministic. I expressed this as the intersection must be the null set. Labels appear exactly once per outgoing edge, and this is all relative to one state. I can have as many 0 edges as I want. They just all have to leave different states. Okay. NFAs have no such restriction. We also get one extra free bonus thing. This is, you can prove this. I would just leave this as an exercise to you. We're now allowed to change states with no input. So I'm allowed to express an automata that has the empty string on one of its edges.
So how state is an empty state?
The states aren't empty. The states are the same states we had before. The label on the edge. So states correspond to nodes.
Yes.
Transitions correspond to edges. Our edges are labeled with previously letters. Now I can also have no letter on one. Why is that? Well, it's not too confusing to imagine like, oh, I can create like a bunch of dummy states that hold the same value and it's logically equivalent. We're just going to say as a convenience I'm allowed to use the empty string to move in between states, and that's allowed. If my slides work, I will have an example that shows why you can do this, but we'll see. Versus a DFA, well, not really versus a DFA, but very similar to union, actually. In an NFA, we accept if any of the non-deterministic paths reaches an accepting state, which kind of makes sense. So if I pull back up, so bad. If I pull this back up, right? I even want it to be like white on a black background, but I don't even know how to do that in paint, right? It is completely possible in the lower NFA to stay in Q1 on a null terminated string, because I'm allowed to follow that 0 back to Q1 as many times as I want and never go to Q2, even if my last letter is 0. It is not required that every possible combination of states ends in the terminating state, or the accepting state. It's only required that there exists some sequence of states which ends in the terminating, or in the accepting state. So you only have to be correct one time of all of the possible branches. This is similar to taking the all. I saw you write an all earlier in one of your list comprehensions or set comprehensions. We don't need all, we need any. Oh, I closed Python because my computer's struggling. It is still quite warm. I might just not be able to use my computer. We might just be doing purely theoretical lectures off slides, which is too bad because I have a bunch of fun things I can show. Okay, Python's fast because Python's not resource intensive. Okay. So the only thing you need is, you just need the any of. And does that work? No.
Should be in set, right?
Should be over set or list. Any Python collection, right? So this is the set version, right?
Can it be in dictionary?
Probably. Dictionaries get pretty weird pretty quickly because of how they deal with duplicates.
No, I don't think so.
I think this is legal Python. Let's find out. I'm committed now.
It will be more complicated with dictionary.
Yeah. Yeah, but that's fine.
Oh, I know.
Because it just only looks at the keys. It ignores the values. So it's the same as a set internally. Okay. Might be multiple paths. Okay. Find a string accepted by the NFA that is rejected by the DFA. We already did this. That's the null terminated string example. Remember that? We take the string 1, 1, blah, blah, blah. We can't actually see this. But let's come over here. What is a string that is accepted by the NFA but not the DFA? 0, 0. 0, 0. If I do that here, 0, no. No, I fall off. Yeah.
It will be end.
Yeah. I fall into the abyss. Right. Easy enough. It's more powerful. Right. That's all there is to it. I was sure I went through and fixed all of these last night. I'm so sad. Okay. Okay. Here's something I'd like you to think about. How do we tell if I give you the 5 tuple Q1 or set of states, the set of letters, the delta function, the initial state, and the accepting states? How do you tell if I've given you a DFA or an NFA? What do you look at? What do you examine? What do you check?
The value of can you
Okay, I'm giving you the tuple,
tuple, yes.
states, letters, transitions, start, and accept. How can I inspect these 5 things and determine if I have a deterministic or non-deterministic finite automata?
By the list, I guess.
Which list? list. Perhaps one from this list. I have a set of states. Does that differ between deterministic and non-deterministic? Do the letters differ? We know the letters don't differ. We've already seen that example, right? Does the initial state differ? Not really. You start in the same place. Does the accept state differ? Not really. You start in the same place. The difference is on delta. So how do we examine delta and see if it differs? Well, what is the thing that makes, what is the invariant that deterministic finite automata have? Well, the deterministic finite automata, I said, they had this intersection equals null set feature over outgoing edges. So we can express that somehow. If I were to write down a non-deterministic finite automata, what would make it non-deterministic is that there is some combination of a current state and a letter that corresponds to more than one new state. So what that means is that my dictionary elements are actually a different type. This is a DFA. What makes it a DFA? Q1 is a state, 0 is an input symbol or a letter or a character or a digit. And each combination of state and character has a unique new state to which it maps. It either goes to Q1 or Q2. We can express this as an assert statement. All of the types. This is the dictionary. Dictionaries, as we just saw in this example, these things can't contain duplicates. Duplicates are deleted. So if I try to say 0 corresponds to more than one possible thing, that's simply not allowed. There's only one possible way. So the Python types system actually enforces determinism with this methodology. So how do I solve that? Hello. Oh, it's almost lunchtime, isn't it?
Just want to check on you.
Yeah, welcome to campus. All of my, here, let me show you something, because I'm embarrassed by it, and I want you to see it. All of my finite automata scale differently on the smartboard than they do when I make them at home, so I'm drawing them in paint.
Yeah. So I use this for my presentation, so what we did to help with the screen is to turn off the lights.
Yeah, we were back and forth on that. We talked about it. Yeah, I don't know, but we've been comfortable so far.
Did you try?
Yeah, we tried it.
Okay.
Yeah, we did it for like an hour and then we turned it off.
Okay.
Or turned them back on. Yeah.
Okay.
How are you doing today?
I'm great. How are you? Did you both sleep well?
Yeah.
Yes.
Did you get your I-20 yet?
Yes, I can.
Okay, that's good.
Stuff.
Anything else?
No.
Okay.
Do you know what a deterministic finite automata is?
Yes,
All right, we'll keep going. Okay. Okay. So we can check to see if a finite automata is deterministic or non-deterministic by examining its delta function. By examining its delta function, we can conclude if there is a unique state that corresponds to each pair of start state and input symbol. And if there is a unique state, then the automata can only go to that state. And if it is not a unique state, then it is non-deterministic. We do not know to which state it goes. That's the difference. I don't know what was making that sound. Okay. Because of my research area and my research interests, I must provide an aside here. When I was reviewing Professor Sipser's lecture, it was very interesting. He said, of course, non-determinism does not exist in practice. And I said, yes, it does. Modern hardware does the Firefox problem that I talked to you about. It executes non-deterministically. Because transistors got so small and so fast, most modern processors have mirrors of themselves. And so when they get to an if statement, and they're not if statements in assembly language, right? They're branch if equal statements or they're jump statements. A modern processor is trying to work ahead of its computation and load memory. So it's moving ahead, it's working ahead, and it doesn't know the results of every computation when it evaluates them. It will figure them out later. It's called things like out-of-order execution, things of this nature, right? So sometimes a modern processor is reading a series of things, and it starts doing a computation, and the computation is a division, so it's really hard, so it doesn't want to wait for it to finish. And then it sees the next statement is an if statement, and within the if block, it reads a different piece of memory than the other piece of memory, right? So maybe we're going to say, hey, if this password is correct, and we'll probably check to see if the password is correct for the division, because it's cryptography, load this web page, and otherwise load that web page. Well, a modern processor is going to simply load both web pages and not show them to you until it's time. So it actually is executing non-deterministically. And historically, what was thought prior to the Spectre meltdown bugs was that, well, you know, the computer has both of those web pages or those memory locations or whatever ready, but you couldn't possibly ever see both of them. And then someone came along and said, well, actually, we can see both of them because we saw they got loaded into cache. So they got pulled off of the disk into the cache or into RAM or something. And because of other security vulnerabilities, we can see any of the memory in cache using something called flush reload, right? So actually, essentially, modern computers are non-deterministic, and it's a huge problem. And so I thought it was very interesting that Sipser was like, yeah, they'll never be non-deterministic computers. And it's like, no, there are, and it's a disaster, and it's my problem. And it was like my doctoral research area that there is just no law that says you can't take all of the silicon you made to do the processor, make an exact copy of that silicon, copy everything over, and execute both branches at different values. And you can do that until you run out of silicon. And this thing has 32 processors in it, which means it can branch 5 times before it has a problem, right? Before it even slows down. Now, I suspect what's going on with its heat right now. I think it ran out of branches, right? It guessed too many things. But in fact, there are physical existing devices that use non-determinism. And I say speculative execution is this hardware technology that corresponds to non-determinism. So I claim this does exist. And I claim it's a huge problem. Separately, this is not the exact same idea, but it is now the case that with something like containerization or something like that, it is very easy to write a Python script, load it in a container, put the container on AWS, and give that container 4 trillion different inputs. And AWS will run all of them. And that's very, very close to non-determinism, right? It's not true non-determinism that can scale to infinity, right? But we can definitely not always have to pick which of 2 routes we're going. And in practice, it is not common that every single transition has some non-deterministic things. In computers, the only things where we'd see non-determinism are basically if statements. And you could argue while loops and for loops, right? This is the XKCD slide summarizing how speculative execution happens. And they use the example of the famous philosophical trolley problem. A runaway trolley is coming down a tracks, and there's people tied to the tracks. And it is going down a track where it will hit 5 people, and you can throw a switch and hit 1 person. And this is like a philosophical problem, because you have to decide whether to throw a switch or not, right? Randall Munroe, who writes XKCD, said, the way speculative execution works is that actually the trolley splits in half, goes down both tracks. And then once you make the decision which track it went down, one of them is reversed, and that trolley disappears and those people come back to life. And that is basically how it happens, right? Because modern processors are not like trolleys. Those are electrons. Electrons can be in 2 places at once. They're quantum particles, right? So like, there's no rules that we actually can't do things like superpositions, or at least model superpositions on modern computers, right? And then the hope is that when you go back in time, all those people come back to life, and then the spectrum meltdown problem was in fact, oh, you can leak something very sensitive before those people come back to life and actually have the security problem. So that's how speculative execution works. Here's 3 ways of thinking about this. This is the way to think about it because it's easier. Of course, you can import the multiprocessing library into Python, and before every single if and for statement, you can create a new branch, and you can execute whether that branch predicts or not, and you don't ever actually have to find the results of a Boolean computation. You can simply execute every possible way through your program of arbitrary computational complexity, and it'll be much slower than Python, but it is possible. So this is in fact possible to do. You can always fork a parallel thread. And then Professor Sipser used the notion of raising a flag. Well, what you really do is, as soon as one of the parallel threads hits the accept state, it sends a kill signal to all of the other threads, and the program resolves amicably. What's the problem with this? Well, what if none of the threads ever execute? Then you've just fork bombed yourself, right? That's essentially writing a virus. The mathematical notion is a little bit easier. I don't find it necessarily particularly hard because we have to deal with infinities in our everyday life all the time to imagine a graph with an infinite number of nodes. That's just a little bit too easy for me to think about. So you can always think of this as like, well, the computation is just some graph, and the graph might have an infinite number of nodes. None of these are as helpful as the magical way, which is that you assume whatever branch you took is the one you needed for your proofs to make sense. And you're allowed to do that, because there's no reason not to. It's non-deterministic, right? So you can just say, well, under the maximally favorable conditions, this could happen, and that is sufficient, right? And so that's the null terminating string example. It's just, this thing will accept if there's null terminating strings by magic, and it does. Nothing is compelling, specifically the exact final 0 to go to Q2. But I can just say, I'll assume it always does. And that is completely reasonable. Let's build delta. We only alter delta. Delta is the only thing we care about. And the only thing we care about is now, instead of going from a state and a letter to a new state, we're going to go from a set of states and a letter to a set of states. And the set of states are the possible states we can be in, because we can be in more than one possible state at a time. We don't know what's going on inside the computer anymore. There's magic going on there. DFAs consider individual states. So, how are you with formal mathematics? Do you know what a codomain is? Okay, don't worry about it. So I have a function. It's going to output values. The set of those values is the codomain. That's what codomain is. The set of destination.
Set of
Destination.
destination.
The set of possible outputs.
Possible.
Yeah. So the set of destination of addition over the natural numbers is the natural numbers. That's the codomain. The codomain of subtraction over the natural numbers is the integers. So we have our DFA that's codomain of its delta function is the set of states, because it can go from any state to any other state. That's a power set. With a NFA, you can take any state and any input, and you're going to get a set of states, the set of possibilities, all possible values of internal programs. And in fact, I've waffled on this a little bit. You can also argue it's from the set of states to the set of states. So you can either say state to set of states or set, but the only important thing is the set of states comes out. I use P, the script PQ, to denote the power set. Do you know what power set is? It's the set of all the possible subsets. Yeah, so if I have 0, 1, the power set is null set, set of 0, set of 1, set of 0 and 1. Yes.
1, 0.
There's no orders because they're sets. So 1, 0, and 0, 1 are the same set.
Same.
Yeah. So there are 4.
4.
Yeah. So the power set is, I'm using R here to denote a set that isn't S. So this is the set R. All sets are such that R is a subset of Q. Q is the set of states, such as 0, 1. R is the subset of set of subsets of that, right? So 0, 1. It's all the combinations, all possible combinations of sets. I think of this as a bit string of the length equal to the number of sets, or of states. And I have a 0 if I can't possibly be in that state, and I have a 1 if I can't possibly be in that state. And that's very simple. So this thing is exactly, if I have n states in Q, this is of size 2 to the n. I wonder if I'll be able to fix these graphics over lunch. But this one we can actually see. Right, what's going on here? We can highlight the only interesting bit. You can go either place with 1. How do we represent that? That's a set.
Set.
Those aren't values, those are sets. Or they are values. Right? That's the only difference. And up here previously we were just putting values there instead of sets. It's set theory all the way down, I'm afraid. We're just doing set theory all day, every day. Okay. I think we should also alter the set of inputs, right? So the set of inputs are the values we conveniently provide to a function. Delta, the initial delta we had from DFA, so we can only accept a single state. Problem is now we have multiple states. So our delta needs to be able to handle that. No problem. We have DFA delta. We are now going to take a set of states and an input character and go to a set of possible output states. How are we going to do that? There's a lot of ways to write this proof. It happens to exactly be set comprehension. So I just say for state in the set of input states, apply delta. That'll give me a set of output states, and then I just union them. I just union them all together. Yeah. So if my input states are 0 and 1, and those can map to 3, 4, and 5, and 5, 6, and 7, and I just take 3 through 7. I don't care that I saw 5 twice. It doesn't affect me.
All the possible outcomes.
All the possible outcomes from any of the possible, right? The computation branches very rapidly, intellectually, if we think of it that way. In practice, we know what programs look like, which is they have relatively few branches. And the branches are very computationally important, but there are relatively few of them. Most of what computers do is move things in and out of memory and perform arithmetic, right? So it's not that bad to branch every time. This is how I express it. Remember, we extracted delta from MQ. So we just took d of q of a. You remember I wrote this as a lambda expression.
Lambda.
And the difference between what I'm writing here and the lambda expression is here I have type hints, because I wanted to do that. M is d of a, q is a state, a is a letter. We're going to return a state. Okay, what's going on here? Same thing, we extract delta. We're going to apply delta to all of the q's in the input state for q in the q's, right? And then we're going to return the set of all of the outputs. So this is just a set comprehension. You can also write it as a for loop with a union. It doesn't matter. It's all logically equivalent. This is considerably more work than that, right? That's why we just say magic. Right? I'm just going to use magic. Yeah. Can do this with lambda. Here's the lambdas. Okay. Before we break for lunch, we're going to show that any NFA language can be recognized by a DFA. How am I going to do that? I'm going to take an NFA. You never guess what I'm going to do. I'm going to use almost the exact same trick I used with union. Remember in union I said, I have two DFAs and I have to keep track of both of these at the same time. Now I have an arbitrary number of the same DFA. That's not so bad, actually, right? So I just take that starting machine and I say, you know what? I'm just going to make a DFA that corresponds to the NFA. It's just going to keep track of all of the same things. I'm going to use the same insight with delta. I'm going to take my DFA, which corresponds to my NFA, and say the states of my DFA is equivalent. I have one of them for each element of the power set of the states of the NFA. Why is that? Well, the delta of the NFA reads elements of the power set. And my delta of my DFA reads individual states. So I say, easy, I am going to have one state that corresponds to each element of the power set. Does that make sense to you? You look a little confused, but you might be understanding it as you got it.
It's just confusing, right?
Okay. I'm going to type. Okay. So I have an NFA. I'm going to denote its states this way. Just the Q of NFA. It perhaps has states 0, 1, and 2. The DFA Q is going to have a state that corresponds to each element of the power set of value. So it's going to have a state that corresponds to the null state, which I'm going to note with underscore. So no states. Because the null set is a subset of the set 0, 1, 2. Does that make sense?
1 and 2. How is a subset of all it?
So the null set is the subset of everything, right?
Oh,
Right? Okay. Then we have all sets of size 2. And then we have the one set of size 3, which is just this thing. How can I express this? It's not too bad. I can use a bit string. I can say, if my element of the power set contains the 0th, 1th, or 2th element of the set, you say sets aren't orders, I say no problem, given any ordering of the set.
okay.
And what happens really quick? Well, actually, this power set is, and you see what I'm doing here. No problem. Those are binary numerals representing set membership. So that means that the size of the set of states of the DFA is 2 to the power of the size of the set of states of the NFA. Exponentially more memory is required. And that's fine, because that's still finite. Anything. Because 2 to any finite number is still finite. I'm closed under exponentiation by 2, right? How many is this? How can we represent it? That's what we talked about. Sigma is unaltered. What this means is that the delta of the DFA, which is supposed to go from state to state, is identical to the delta of the NFA, which goes from set of states to set of states. Because my states are set of states, it's the same thing. The only difference is I have to have way more states in my DFA, but all of the calculations are the same. Right? Does that make sense? I love that. It's the same delta. You only change the states. We do have to be a little more careful with F, the same way we had to be careful with F, with the set, which is that the accepting states of the DFA are all power sets where the intersection with the accepting states are non-zero. So that is any element of the current set of states is one of the accepting elements. Not too bad. We just use a little intersection. Say, oh, the same thing's in both of these, therefore one of them accepts. And I consider that a proof. So I've written this down as a proof, and I feel great about it. You could argue we've taken liberties with delta. I don't know, right? It depends on what you mean with the mathematical object state. When I learned complexity theory, we were very strict that all states were equal, but there was a labeling on states, so there was a labeling function. Then you have to fiddle around with the labeling function here. I haven't said that. I've said these are just abstract mathematical objects, and I can work over them however I want, right? And actually, that's not that different from having something with a labeling function, right? So these are all logically equivalent. And with that, it's time for lunch. Do you want to go find some of the Indian food from last night?
Yeah, the cauliflower.
Yeah, the cauliflower. I'm going to try and get my computer to be cooler, and then we can do anything. But yeah, I can't talk anymore, so we have to end tonight.